All right. Let's see. Where did we leave off? Oh, so we're on memory allocation today. I'm gonna need a little bit more light to read in here, but yeah, memory allocation. And I have the PDF up here, so we're ready to go. Just let me turn the light on here. Let's see. I got a remote for this thing. Alright, that is good enough for reading. Alright, I don't really know exactly what we're going to be talking about here, but given the title of the chapter is memory allocation, it's probably a bunch of heap stuff. Yeah, malloc free break. Break, I guess, grows the size of the heap. Some alternative calc allocation. Oh, you got allocate memory on the stack. I've never used that function before. But yeah, not a super long chapter, so let's dive into it. Memory allocation. Many system programs need to be able to allocate extra memory for dynamic data structures, e.g. linked lists and binary trees, whose size depends on information that is available only at runtime. This chapter describes the functions that are used to allocate memory on the heap or on the stack. Allocating memory on the heap. The process to this light is horrible. I really should get like a... Well, I do have an extra light. It's in the closet though. Alright. Let's see. The process can allocate memory by increasing the size of its heap. A variable size segment of continuous virtual memory that begins just after the initialized data segment of a process and grows and shrinks as memory is allocated and freed. See figure 6.1 on 119. I'm just going to go back there and get it real quick. Yeah, so at the bottom we have text, initialized, uninitialized data, and then the heap. All right. The current limit of the heap is referred to as the program break. To allocate memory, C programs normally call the malloc family of functions, which we describe briefly below. Which we describe shortly. However, we begin with a description of bork and sbork, upon which the malloc functions are based. Adjusting the program break, bork, and sbork. Resizing the heap, i.e. allocating or deallocating memory, is actually as simple as telling the kernel to adjust its idea of where a process's program break is. Initially, the program break lies just past the end of the uninitialized data segment, i.e. the same location as end, shown in figure 6.1. Boop. After the program break is increased, the program may access any address in the newly allocated area, but no physical memory pages are allocated yet. The kernel automatically allocates new physical pages on the first attempt by process to access address in those pages. Traditionally, the Unix system has provided two system calls for manipulating the program break, and these are both available on Linux break and sbreak. Although these system calls are seldom used directly in programs, understanding them helps clarify how memory allocation works. Okay, we got our little source code here. We can pull this down from, I'm guessing this is it. I don't know, he has a, oh, okay. Let me move my desk back a little bit. I think that might help the lighting situation. Then I'm gonna move this camera so the display is not in the way. Bam. Alright. So break, you give it the end of the data segment, which is a void pointer. Actually, give me 1 second. I need to disable locking on my streaming PC. Because for some reason, it died earlier today. Let's see, trigger, toggle, idle lock is disabled. Toggle screen shaver too. Oh. Okay, cool. So the break, you just tell it where you want the data segment, what address you want it. It returns 0 in success, -1 error. S break gives you a pointer back, and you give it an increment. You say, I want to go up by a certain amount, like a size. It returns the previous program break on success. Okay, so I guess if you want to know, I guess that makes sense. You can calculate where the new break is. Or you can pass in 0 here and it's a read. Cool. Alright, the break system call sets a program break to the location specified by end data segment. Since virtual memory is allocated in units of pages, end data segment is effectively rounded up to the next page boundary. Attempts to set program, so the interface is a pointer. Pointer to any byte in the if it's byte addressable memory, it'll be any byte in memory, but since virtual memory is allocated in units of pages, end data segment is effectively rounded up to the next page boundary. All right. Attempts to set program break below its initial value, below end, are likely to result in unexpected behavior such as segmentation fault, SIG-SEG-V signal described in section 22 when trying to access data in now non-existent parts of the initialized or uninitialized data segments. The precise upper limit on where the program break can be set depends on a range of factors, including the process resource limit for the size of the data segment, the R data limit, R limit data. Let me reread this. The precise upper limit on where the program break can be set depends on the range of factors, including the process resource limit for the size of the data segment. R limit data. I'm confused because like this isn't the data segment. This is the heap. Is the heap part of the data segment? I don't think so. No, let's ask AI. Hello? No? Not gonna do it? There you go. Alright. Is the heap is heap memory in C/Unix considered part of the data segment? Yeah. So then why is R, why does R, what was it called here? R limit data. Let's see. limits the process data segment, and historically the heap was implemented as part of the data segment. I didn't know that. That doesn't make sense. Even today, Linux still treats the break-based heap as data for accounting purposes. R-limit data dates back to early Unix, where the process had essentially text, data, and heap in a stack. Okay. Keep points data plus BSS, and RO data, and the heap were one contiguous region. Heap grew upwards using break as break. There's no memmap allocator design yet. So data segment historically meant everything was writable and non-stack. So read only doesn't factor into that. Interesting. Okay. Okay, that's enough of that. Let's continue reading. R limit data described in section 36.3 and the location of the memory mappings, shared memory segments, and shared libraries. A call to sbreak adjusts the program break by adding increment to it. On Linux, sbreak is a library function implemented on top of break. The int ptrt type used to declare increment is an integer data type. On success, sbreak returns the previous address of the program break. In other words, if we have increased the program break, the return value points to the start of the newly allocated block of memory. The call sbreak0 returns the current setting of the program break without changing it. This can be useful if you want to track the size of the heap, perhaps in order to monitor the behavior of a memory allocation package. susv2 specifies break and sbreak, making them legacy. susv3 removed their specifications. Oh, interesting. Allocating memory on the heap, malloc, and free. In general, C programs use the malloc family of functions to allocate and deallocate memory on the heap. These functions offer several advantages over break and sbreak. In particular, they are standardized as part of the C language, are easier to use in threaded programs. Provide a simple interface that allows memory to be allocated in small units and allows us to arbitrarily deallocate blocks of memory which are maintained on a free list and recycled in future calls to allocate memory. The malloc function allocates size in bytes from the heap and returns a pointer to the start of the newly allocated block of memory. The allocated memory is not initialized. Includes standard lib h, malloc, size t, returns a pointer to the newly allocated memory on success or null on error. Oops. Boom. Because malloc returns void star, we can assign it to any type of C pointer. The block of memory returned by malloc is always assigned to on a byte boundary suitable for efficient access on any type of C data structure. In practice, this means that it is allocated on an 8-byte or 16-byte boundary on most architectures. susv3 specifies that the call malloc0 may return either null or a pointer to a small piece of memory that can and should be freed with free. On Linux, malloc0 follows the latter behavior. If I want to malloc0, okay, that seems weird. If memory could not be allocated, perhaps because we reached the limit to which the program break could be raised, then malloc returns null and sets error no to indicate the error. Although the possibility of failure in allocating memory is small, all calls to malloc and the related functions that we describe later should check for this return error. The free function declares the block of memory pointed to by its PTR argument, which should be an address previously returned by malloc. or one of the other heap memory allocation functions that we described in this chapter. So if you give it a void star pointer, how does it know how much to free? In general, free doesn't lower the program break, but instead adds the block of memory to a list of free blocks that are recycled in future calls to malloc. This is done for several reasons. The block of memory being freed is typically somewhere in the middle of the heap rather than at the end, so that lowering the program break is not possible. It minimizes the number of S-break calls the program must perform. As noted in section 3.1, system calls have a small but significant overhead. In many cases, lowering the break would not help programs that allocate large amounts of memory, since they typically tend to hold onto allocated memory or repeatedly release and reallocate memory rather than release it and then continue to run for an extended period of time. I guess the kernel or the standard library or the kernel maintains some type of mapping of pointers to how big the allocation was. That's my only guess for why free doesn't have to specify the size. That means that malloc and free are probably not syscalls. Let's see. Man syscalls is malloc or free. Free huge pages. PK free, SRM honestly free. Malloc. Nope. Man2 malloc. Nope. So it's all implemented through break and sbreak, and malloc must track. So man free, not free 1, free 3, I think. Yeah. Free frees. The free function frees the memory space pointed to by p, which must have been returned by previous call to malloc or related functions. Otherwise, or if p has already been freed, undefined behavior occurs. If p is null, no operation is performed. Let's ask the AI. The signature for free is, oops, come on, you can copy, I believe in you. All right, why do you not have to provide the size of the block to free? Is that stored in glib or say libc? Let's see, where's my thing at? Yeah. Short answer, yes, the allocator stores the size and other metadata for you, and free uses that metadata. You don't pass the size because the allocator already knows it. Long answer with concrete details. Where does free get the size? When you call malloc 100, the allocator does not hand you 100 raw bytes, internally allocates a larger block that looks conceptually like this. Allocator metadata, user memory 100 bytes. Oh, so there is metadata right before it in memory. Cool. The metadata, often called the chunk header, typically stores things like size of the block, whether the block is free or in use, flags, arena info, memmapped versus heap, etc., links for free lists when freed. When you call free, free does something like subtract a fixed offset from P, recover the allocator's header. Okay, it just throws it at a fixed offset. Interesting. Read the stored size, return the block to the appropriate free list arena. Okay. So the size is not tracked by libc globally, it's stored adjacent to the location itself. Interesting. Yeah. I wonder if we can read that. I'm just kind of curious here. So CD into chapter 6. Do I have anything going on here yet? No. Let's do something like free header dot c. And I'm just gonna like create my main. We need standard lib, include standard lib.h, and then we're gonna call free on null here, just the go-to definition, and that takes us here. Free a block of allocate by malloc realloc or calloc. Is this thing? Wow, is this the definition here? No way. No. This is no definition. This is a for declaration. Where is free implemented on a standard glib Linux Arch machine? It's called malloc C. Yeah, it's already compiled. I can obj dump it. Stop. Is glib C source code normally on installed somewhere on Linux file system, or just headers with the object code? Okay, that's why. Well, we know it's called malloc.c, so maybe we, oh, that's not what I wanted to do. Damn it. Go back here. 7. Oh, we're in chapter 7. I'm in the wrong directory here. MV free header, chapter 7, which doesn't exist. There we go. There we go. rsync abcci chapter 6 into here, and then rmr fref proc, delete all those, make clean, cat clang d cat make file, cat get ignores, make sure these are clean. That clang D I need to fix, because I never was able to figure out how to make this generic. 7, and then the make file here, local targets I can delete, everything else is good. Make clean, cool. lt ref -L9, yeah, that's just the lib. Cool. Make. All right, so what were we doing here? I wasn't able to find the implementation for free, but I wanted to decode the header, so let's call this thing, yeah, free header, and then let me close this out. So I'm gonna have to malloc, and I want it to do a unique integer that I'll recognize, and it's gonna be in hexadecimal. So how big is feed? Let's see, Python 0x feed. It's 65,000. That's not that big. That's fine. So we'll malloc up a feed. We'll just ask this in C, can you do hex literals? Okay. Cool. 0x feed will be our size of our malloc, and it gives us back a void star. PTR. We'll just continue to call it a void star. And then attempt to read the memory behind it. We'll read the 8 bytes behind it and see if we recognize feed anywhere. So how do we do that? Print f bytes before will be %x, I think it is. And then we'll give it the dereference to PTR. but we have to tell it what it is. So maybe we'll call this a void star a char array of 8, maybe like that. And then here we can minus the pointer. How do you move back? I can do negative. No, I can't do -1. Given an array and see how do you address an element before the array starts. Is that possible? Can use pointer arithmetic. Undefined behavior. Yeah, I think -1 should work. Let's try that. We'll call it PTR -1. No, because the character is let me try to figure this out. So I have a void star. I'm going to turn it into a char star. And then what I actually want is a long star. And then this will be negative. Or should we do negative here? And then dereference that. Like that. Nope. Call to undeclared. Oh. Standard IO. Now we're saying format specifies type unsigned int, but the argue because I need to do LX. And then make build free. I got FF. Not exactly what I wanted. Maybe we call this multiple times. Let's try. Let's try doing it a second time. Yeah, why not? Oops. Make it first. I need a new line. This number has to exist somewhere if it's make. Yeah. I don't think it's stored there, bro. Could be at the end. There's FF01. Like, that's definitely not the value at all. So we can go to the end of it. So we could say something like, did all this PTR, and then we're going to add, I don't know if you can do this, add 0x feed, and then dereference that. Immediately segment it. Okay. Can you write me C code that will take a void, a pointer, allocated with malloc and print the memory for the header that contains the size of the allocation that free then reads. Yeah. So you malloc and they just do -1. So maybe we try doing all that. Oh, and you got all this stuff here. Copy code. I'm just gonna copy this whole thing. Oops. So the request, I'm gonna say 0xFED. Make size raw. See, it gets the size wrong. Python. Oh, it's higher because of those bits that are set. Maybe. Let's try that. Python 0xFED 65,261, and it gave us back 65,261. What's the size of size t? Man size t. Unsigned integer type callable size max. Okay, man size max. Is that a thing? No. Free header. Well, I'm gonna delete this stuff up here. Boom. I don't think I need that anymore. That's not. I'll leave it. Why not? I'm gonna go to definition on this size t. See if I can figure out, at least from the header, how big it is. Size type size t. How big is size t? I think it's 64 bits on 64 bit. Has to be 64 bit, right? Yeah. Okay. All right. Enough monkeying around there. Oops. Cool. All right. Let's go back to reading this. Boom, boom. we were on where are we at? Free example program here. If the argument is given to free is null pointer, then the call does nothing. Why does it keep on pulling down like that? I don't like that it does that. Why? Stop it. Then the call does nothing. In other words, it is not an error to give a null pointer to free. Making any use of pointer after the call to free, for example, passing it to free, a second time is error that will lead to unpredictable results. In general, free doesn't load the program break, but instead, yeah, okay. Yeah, okay. Example program. The program listing 7.1 can be used to illustrate the effect of free on the program break. This program allocates multiple blocks of free memory and then frees some or all of them depending on its optional command line arguments. The first two command line arguments specify the number and size of blocks to allocate. The third command line argument specifies the loop set step unit to be used when freeing memory blocks. If we specify 1 here, which is also the default if this argument is omitted, then the program frees every memory block. If 2, then every second allocated block, and so on. The fourth and fifth command line arguments specify a range of blocks that we wish to free. If these arguments are omitted, then all allocated blocks in steps given by the third command line argument free. Okay, great. This is the ME malloc free and S break. LT, yeah. CD ref. MKDAR, this is under ME malloc. And then here, there should be this guy here, yeah. Oh. Oh. Come on. Copy link address. wget. Bam. Make warning. I think default source is what I need to give that. As Burke. This would be called default source. Cool, make. Yep. Build free, not free. Ref. ME malloc free and S break. Number of allocs, we want to do 10 allocations, block size of 100. The free will be every second. Yeah, and it didn't cause that to move. But if we did like 10,000, still, we did 1,000 times 10,000. And if we did this, we went back down. Okay. Running the program listing 7.1 with the following command line causes the program to allocate 1,000 blocks of memory and then free every second block. That's pretty much what I was doing. It's funny. 1,000, and then he just did 10.24.0 here. Yeah. And that doesn't actually set the break lower. The output, oops, I need to go back here, sorry. The output shows that after these blocks have been freed, the program break is left unchanged from the level it reached when all memory blocks are allocated. Yep. The following command line specifies that all but the last of the allocated blocks should be freed. Again, this program remains at its high watermark. So yeah, you can say, okay, I want to free everything, which would be 1, and it'll actually reset the break. But if you say 1, 1, if I do 10, 24, 0 here, or no, that's the number. If I do 1000 here, it'll reset it. If I do 999 here, it can't, because that high watermark. Yeah, cool. If, however, we free a complete set of blocks at the top of the heap, we see that the program break decreases from its peak value, indicating that free has been used as break to lower the program break. Here, we free the last 500 blocks of allocated memory. So we do 500 to 1000, and it'll lower it, but not all the way. Cool. In this case, the glibc free function is able to recognize that an entire region at the top of the heap is free, since when releasing blocks, it coalesces neighboring free blocks into a single larger block. Such coalescing is done to avoid having a large number of small fragments on the free list, all of which may be too small to satisfy subsequent malloc requests. Let me reread that. In this case, glibc free function is able to recognize the entire region at the top. Okay, since when releasing blocks, it coalesces neighboring free blocks into a single larger block. Such coalescing is done via having a large number of small fragments on the free list, all of which may be too small to satisfy subsequent malloc requests. Okay. The glibc free function calls sbreak to lower the program break only when the free block at the top end is sufficiently large, where sufficient is determined by parameters controlling the operation of the malloc package. 128 kilobyte is a typical value. This reduces the number of sbreak calls, i.e. the number of break system calls that must be made. To free or not to free? Let me go over here. Zoom in to this real quick. Oh, too much on that one. Let me go over here. Just test one thing real quick. All right. See. Trying to figure out the YouTube streaming stuff. I'm very new to this. And it is confusing. Let's see here. Test, test. Test, test. Well, I'll figure this out later. I wanted a way to like see the streaming preview for YouTube, but I can't figure it out for the life of me. All right, anyways, let's get back to reading here. So free, basically, if you have a block at the end of the heap, it'll call sbreak to reset it if it's sufficiently large. So to free or not to free, when a process terminates, all of its memory is returned to the system, including heap memory allocated by functions in the malloc package. In programs that allocate memory and continue using it until program termination, it is common to omit calls to free, relying on this behavior to automatically free the memory. This can be especially useful in programs that allocate many blocks of memory, since adding multiple calls to free could be expensive in terms of CPU time, as well as perhaps being complicated to code. Although relying on process termination to automatically free memory is acceptable for many programs, there are a couple of reasons why it can be desirable to explicitly free all allocated memory. Explicitly calling free may make the program more readable and maintainable in the face of future modifications. If we are using malloc debugging library described below to find memory leaks in a program, then any memory that is not explicitly freed will be reported as a memory leak. This can complicate the task of finding real memory leaks. Yeah, I mean, that's immediately what came to mind for me. I was using Valgrind or something. All right, implementation of malloc and free. Although malloc and free provide an interface for allocating memory that is much easier to use than break and sbreak, it is still possible to make various programming errors when using them. Understanding how malloc, so when people say they implement their own memory allocator, is it that memory allocator is calling break and sbreak and just skipping past all this libc malloc free stuff? I wonder if that's the case. Understanding how malloc and free are implemented provides us with insights into the causes of these errors and how we can avoid them. The implementation of malloc is straightforward. It first scans the list of memory blocks previously released by free in order to find one whose size is larger than or equal to its requirements. Different strategies may be employed for this scan depending on the implementation. For example, first fit or best fit. If the block is exactly the right size, then it's returned to the caller. If it's larger, then it is split so that a block of the correct size is returned to the caller and a smaller free block is left on the free list. If no block on the free list is large enough, then malloc calls sbreak to allocate more memory to reduce the number of calls to sbreak. Rather than allocating the exact number of bytes required, malloc increases the program break in larger units, sometimes multiples of the virtual memory page size, putting the access memory into the free list. Looking at the implementation of free, things start to become more interesting. When free places a block of memory into the free list, how does it know what size the block is? This is exactly what we're getting ahead of the book on. How does it know what size the block is? It's done via trick. When malloc allocates the block, it allocates extra bytes to hold an integer containing the size of the block. This integer is located at the beginning of the block. The address actually returned to the caller points to the location just past the length value, as shown in figure 7.1. When a block is placed on the doubly linked free list, free uses the bytes of the block itself in order to add the block to the list, shown in so-and-so. So this is a block on the free list, which is a length of block L, pointed to previous free block, pointed to next free block, remaining bytes on the free block of free block. Okay. As blocks are deallocated and reallocated over time, the blocks of the free list will become intermingled with blocks of allocate. So is this... I'm wondering if this free list is stored somewhere outside of the heap, or if it is the actual heap. If that makes sense. As blocks are deallocated and reallocated over time, the blocks of the free list will become intermingled with blocks of allocated and used memory as shown in figure 5.3. Or 7.3, sorry. Head of free list. Okay, it's gonna say pointing over there. Blocks on free list. Okay. That makes sense. So the heap is a free list. Like, there's data encoded in the heap to make it the list. Now consider the fact that C allows us to create pointers to any function in the heap and modify the locations they point to, including length, previous free block, and next free block. Pointers maintained by free and malloc, and this is to add this to the preceding description, and we have a fairly combustible mix when it comes to creating obscure programming bugs. For example, if via a misdirected pointer we accidentally increase one of the length values preceding the allocated block of memory and subsequently deallocate that block, then free will record the wrong size block of memory on the free list. Subsequently, malloc may reallocate this block, leading to a scenario where the program has pointers to two blocks of allocated memory that it understands to be distinct but will actually overlap. Numerous other pictures of what could go wrong can be drawn. Oops. To avoid these types of errors, we should observe the following rules. After we allocate a block of memory, we should be careful not to touch any bytes outside the range of that block. This could occur, for example, as a result of faulty pointer arithmetic or off by one errors in loops updating the contents of a block. It is an error to free the same piece of allocated memory more than once. With glibc on Linux, we often get a segmentation violation seg_v signal. This is good because it alerts us that we've made a programming error. However, more generally, freeing the same memory twice leads to unpredictable behavior. We should never call free with a pointer value that wasn't obtained by a call to one of the functions in the malloc package, like on the stack or something. If we are writing a long-running program, e.g. a shell or a network daemon process that repeatedly allocates memory for various purposes, then we should ensure that we deallocate any memory after we have finished using it. Failure to do so means that the heap will steadily grow until it reaches limits of available virtual memory, at which point further attempts to allocate memory fail. Such a condition is known as a memory leak. Tools and libraries for malloc debugging. Do they talk about Valgrind here at all? No. Failure to observe the rules listed above can lead to the creation of bugs that are obscure and difficult to reproduce. The task of finding such bugs can be eased considerably using the malloc debugging tools provided by glibc or one of a number of malloc debugging libraries that are designed for this purpose. Among malloc debugging tools provided by glibc are the following. The mtrace and muntrace functions allow a program to turn on tracing of memory allocation calls on and off. These functions are used in conjunction with the malloc trace environment variable, which should be defined to contain the name of the file to which tracing information should be written. When mtrace is called, it checks to see whether this file is defined and can be opened for writing. If so, then all calls to functions in the malloc package are traced and recorded in the file. Since the resulting file is not easily human readable, a script also called mtrace is provided to analyze the file produced. Do I have that on my system here? Mtrace, yeah. It's a Perl script, which, oops. Can I do them? User bin mtrace? No. It is a, wait a minute. It's a bin sh Perl. Definitely looks like Perl to me. Man, it's been ages since I wrote any Perl. Ooh-wee. I've never seen this syntax before. So when the shell reads this comment, it's like, oh, I need to like evaluate this function here. That looks like an empty function definition, but here it isn't. And then, I don't know, this looks weird to me. Let's ask AI about this. When I opened user bin mtrace, it has this at the top. Explain it. Polyglot shell plus Perl launcher. The same file is intentionally valid both as bin sh and as Perl. And the shell part re-executes the file under Perl. Let's go line by line. Shebang. Run as a shell script first. When you run, the kernel starts out with bin sh, not Perl. Editor hint, harmless at runtime. Okay. This weird looking eval block. In POSIX shell, it means define a shell function named Q, colon is shell do nothing true, built in. Eval is used to avoid confusing Perl later. So after this runs, shell has function Q that does nothing. Why the odd quoting? That's not odd quoting. The Q block then says exec Perl and this calls the function Q. The function body is colon does nothing. The brace is just treated as arguments to Q. Oh, okay. So it just evaluates it. The trailing column is just termination student. Okay. In Perl, this is where the trick happens. Step by step in Perl, Q. Q is Perl's single quoted string literal. So this just a string containing shellcode. Earlier line, eval. In Perl, eval string evaluates Perl code. So it's a string literal evaluating a string load is nothing, so Perl happily ignores the whole section. This is like some crazy stuff here. Anyways. How many lines is this thing? I've just never seen this pattern before. I don't do a lot of Perl. I do remember this stuff, those subroutines. Arg list. Got some indentation issues there. Okay. We're talking about mtrace. Is provided to analyze the file and produce a readable summary. For security reasons, calls to mtrace are ignored by set user ID and set group ID programs. The mcheck and mprobe functions allow the program to perform consistency checks on blocks of allocated memory, for example, catching errors such as attempting to write to a location past the end of a block of allocated memory. These functions provide functionality that somewhat overlaps with the malloc debugging libraries described below. Programs that employ these functions must be linked with the malloc library using the CC and mcheck option. The malloc check environment variable. Note the trailing underscore serves a similar purpose to malloc check and mprobe. One notable difference between the two techniques is that using malloc check doesn't require modification recompilation of the program. By setting this variable to different integer values, we can control how a program responds to memory allocation errors. Possible settings are 0, meaning ignore errors, 1, meaning print diagnostic errors on standard error, and 2, meaning call abort to terminate the program. Not all memory allocation and deallocation errors are detected via the use of malloc check underscore. It finds just the common ones. However, this technique is fast, easy to use, and has low runtime overhead compared with the use of malloc debugging libraries. For security reasons, the setting of malloc check is ignored by set user ID and set group ID programs. Further information about all of the above features can be found in the glibc manual. A malloc debugging library offers the same API as a standard malloc package, but does extra work to catch memory allocation bugs. In order to use such a library, we link our application against that library instead of malloc package in the standard C library. Because these libraries typically operate at a cost of slower runtime operation, increased memory consumption, or both, we should use them only for debugging purposes and then return to linking the standard malloc package for the production version of our application. Among such libraries are Electric Fence, dmalloc, Valgrind, and Ensure++. I've only heard of Valgrind, and I think I've heard of Electric Fence. Both Valgrind and Ensure++ are capable of detecting many of the kinds of bugs aside from those associated with heap allocation. See their respective websites for details. Controlling and monitoring the malloc package. The glibc manual describes a range of non-standard functions that can be used to monitor and control the allocation of memory by functions in the malloc package, including the following. The mallopt function modifies the various parameters that control the algorithm used for malloc. For example, one such parameter specifies the minimum amount of reusable space that must exist at the end of the free list before sbreak is used to shrink the heap. Another parameter specifies an upper limit to the size of blocks that will be allocated from the heap. Blocks larger than this are allocated using the mmap system call. The malinfo function returns a structure containing various statistics about the memory allocated by malloc. Many Unix implementations provide versions of mallopt and malinfo. However, the interfaces offered by these versions vary across implementations, so they are not portable. Other methods of allocating memory on the heap, as well as malloc, the C library provides a range of other functions for allocating memory on the heap. As we describe those functions here, allocating memory with calloc and realloc. The calloc function allocates memory for an array of identical items. So it's like a malloc v type thing. So calloc num item size t size returns a pointer to allocate memory on success or null on error. The num items argument specifies how many items to allocate, and the size specifies their size. After allocating a block of memory of the appropriate size, calloc returns a pointer to the start of the block, or null if the memory could not be allocated. Unlike malloc, calloc initializes the allocated memory to 0. Okay, that has a cost associated with it, but it is sensible. Here is an example of using calloc. Struct my struct, some field definitions, then I get a pointer on the heap. Yeah, the pointer is heap allocated, but the thing it points at isn't. Then we call calloc. We want 1,000 of those structs, and we assign the pointer into P. Cool. Realloc. The realloc function is used to resize, usually enlarge, a block of memory previously allocated by one of the functions in the malloc package. So we give a pointer, we give it size they want it to be. Returns pointer to allocated memory on success or null on error. The pointer argument is a pointer to the block of memory that is to be resized. The size argument specifies the desired new size of the block. On success, realloc returns a pointer to the location of the resized block. This may be different from its location before the call. On error, realloc. Wait a minute. On success, realloc returns a pointer to the location of the resized block. This may be different from the location before it's called because it might not have free space at the end of it. On error, realloc returns null and leaves the block pointed to by PTR untouched. Test v3 requires this. When realloc increases the size of a block of allocated memory, it doesn't initialize the additionally allocated bytes. Memory allocated using calloc or realloc should be deallocated with free. The call realloc PTR 0 is equivalent to calling free PTR followed by malloc 0. If PTR is specified as null, then realloc is equivalent to calling malloc size. Okay. For the usual cases where we are increasing the size of the block of memory, realloc attempts to coalesce the block with an immediately following block of memory on the free list, if one exists and is large enough. If the block lies at the end of the heap, then realloc expands the heap. If the block of memory lies in the middle of the heap and there is insufficient free space immediately following it, realloc allocates a new block of memory and copies all existing data from the old block to a new block. This last case is common and CPU intensive. In general, it's advisable to minimize the use of realloc. Boop. Since realloc may relocate the block of memory, we must use the return pointer from realloc for future references to the memory block. We can employ realloc to reallocate a block pointed to by the variable PTR as follows. In this example, we didn't assign the return value of realloc directly to PTR because if realloc had failed, then PTR would have been set to null, making the existing block inaccessible. Yeah, that's kind of like a little bit annoying because realloc may move the block of memory. Any pointers that reference the location inside the block before the realloc call may no longer be valid after the call. The only type of reference to a location within the block that is guaranteed to remain valid is one formed by adding an offset to the pointer to the start of the block. We discuss this point in more detail in section 48.6. Not sure what he means by that. Let's reread that. I mean, we'll go into it in more detail later, but because realloc may move the block of memory, any pointers referred to the location inside the block before the realloc call may no longer be valid after the call. The only type of reference to a location within a block that is guaranteed to remain valid is one formed by adding an offset to the pointer to the start of the block. We just got, I don't know about that. Okay. Allocating align memory, memoline, and POSIX memoline. So we got some alignment stuff, and then stack allocation, and then a summary. Cool. The memoline and POSIX memoline functions are designed to allocate memory starting at an address aligned at a specific power of 2 boundary. A feature that is useful for some applications. See, for example, listing 13.1 on page 247. Let's pull it up. 247. See if it's interesting at all. That's not right. 13.1. Oh, it's source code. I thought it was a diagram. I'm not going to read that. All right. Let's see. So memoline, size T boundary. It's a power 2 boundary, like 32-bit, 64. Size T size returns pointer to allocated memory on success or null on error. The memoline function allocates size bytes starting at an address aligned to a multiple of boundary, which must be a power of 2. The address of the allocated memory is returned as the function result. The memoline function is not present on all Unix implementations. Most other Unix implementations that provide memoline require the inclusion of standardlib.h instead of malloc-h. In order to obtain the function declaration, SUS-v3 doesn't specify memoline, but instead specifies a similar function named POSIX memoline. This function is a recent creation of the standards committees and appears on only a few Unix implementations. So, yeah, okay. The POSIX memoline function differs from memoline in 2 respects. The address of the allocated memory is returned in memptr. Okay. Instead of returning a void star. The memory is allocated to a multiple of alignment, which must be a power of 2 multiple of size of void star. 4 or 8 bytes on most hardware architectures. Note also the unusual return value of this function. Rather than returning -1 on error, it returns an error number, a positive integer of the type normally returned by an error no. If size of void star is 4, then we can use POSIX memoline to allocate 65,536 bytes of memory aligned on a 4096 byte boundary as follows. Blocks of memory allocated using memoline or POSIX memoline should be deallocated with free. On some Unix implementations, it's not possible to call free on a block of memory allocated via memoline because the memoline implementation uses malloc to allocate a block of memory and then returns a pointer to an address with a suitable alignment in that block. The glibc implementation of memoline doesn't suffer this limitation. Allocating memory on the stack. Alloca. Like the functions in the malloc package, alloca allocates memory dynamically. However, instead of obtaining memory from the heap, alloca obtains memory from the stack by increasing the size of the stack frame. This is possible because the function calling is the one whose stack frame is by definition on the top of the stack. Therefore, there is space above the frame for expansion, which may be accomplished by simply modifying the value of the stack pointer. The size argument specifies the number of bytes to allocate to the stack. The alloca function returns a pointer to the allocated memory as its function result. We need not, indeed must not call free to deallocate memory. with the alloca. Likewise, it's not possible to use realloc to resize a block of memory allocated via alloca. Although alloca is not part of SusV3, it is provided on most Unix implementations and is thus reasonably portable. Older versions, glibc, and some other Unix implementations, mainly BSD derivatives, require the inclusion of standard libh instead of alloc.h to obtain the declaration of alloca. If the stack overflows as a consequence of calling alloca, then program behavior is unpredictable. In particular, we don't get a null return to inform us of the error. In fact, in this circumstance, we may receive 6-sig signal. Refer to section 21.3 for further details. Note that we can't use alloca within a function argument list, as in this example, func alloca size. Yeah, we say allocate space on the stack, and then we call some func, and we pass that pointer so that new. Why can't we? Why can't we write the stack memory inside a function that we call into? This is because the stack space allocated by alloca would appear in the middle of the space for the function arguments, which are placed at fixed locations within the stack frame. Instead, we must code such as this: void star y alloca size. Oh, you can't do it inline. Is that like an optimization thing? Stack space allocated by alloca would appear in the middle of the space for the function arguments. Okay. Using alloca to allocate memory has a few advantages over malloc. One of these is that allocating blocks of memory is faster with alloca than with malloc, because alloca is implemented by the compiler as inline code that directly adjusts the stack pointer. Furthermore, alloca doesn't need to maintain a list of free blocks. Another advantage of alloca is that the memory that it allocates is automatically freed when the stack frame is removed, that is, when the function that called alloca returns. This is so because the code executed during function return resets the value of the stack pointer registered to the end of the previous frame, i.e. assuming a downwardly growing stack, to the address just above the start of the current frame. Since we don't need to do the work of ensuring that allocated memory is freed on all return paths from the function, coding of some functions becomes much simpler. Using alloca can be especially useful if we employ long jump, section 6.8, or sig long jump. Interesting. Is this the thing that I learned about last night about how, let's see, sig long jump? Probably not. What's it called? JMP. Sig set jump and sig long jump also perform non-local gotos but provide predictable handling of the process signal mask. It's just a signal. I thought it might be signature. That's why that's an optional. Okay. Cool. That makes sense. I saw something on the internet last night where Apple basically like puts signatures inside the pointers of known locations in a binary. So if you like mutate where the pointer is pointing to based on where it's stored, it'll break the signature. Like the address of the pointer, not the pointer. not the pointer itself, like the thing that it's pointing to, but if you try to modify what it points to, it'll break the signature based on bit set and the address of the pointer, which is insane. It's probably some simple like checksum thing, just to like make it difficult to write to it, but not impossible. All right, what are we doing here? Using alloca can be especially useful when employing long jump to perform a non-local go-to from a signal handler. In this case, it is difficult or even possible to avoid memory leaks if we allocated memory in the jumped over function using malloc. By contrast, alloc avoids this problem completely since the stack is unwound by these calls. The allocated memory is automatically freed. Summary: using the malloc family of functions, a process can dynamically allocate and release memory on the heap. In consideration the implementation of these functions, we saw that various things can go wrong in a program that mishandles the blocks of allocated memory, and we noted that a number of debugging tools are available to help locate the source of such errors. The alloca function allocates memory on the stack. This memory is automatically deallocated when the function that calls alloca returns. Exercises: modify the program listing 7.1 free and sbork to print out the current value of the program break after each execution of malloc. Run the program specifying a small allocation block size. This will demonstrate that malloc doesn't employ sbreak to adjust the program break on each call, but instead. Sorry, my brain was thinking about the next one, which is implement malloc and free. So the job of malloc and free is that you have to manage calls to break or sbreak to grow or shrink the heap. You also have to record the size of the malloc somewhere so that when you call free, you can free it, whether that's in a global data structure somewhere or alongside the data itself. Then you need to be able to mark sections of memory as free. And then you need to be able to call sbreak when there's a significantly large amount of memory free at the end of the heap. And then call sbreak to grow it when there's no memory available on the heap. I mean, it's a pretty straightforward job, to be honest. It's not insane. Should I do this exercise? I'm on chapter 8. I got a lot more to go here. And I don't know what I would really learn from it. Maybe I'll come back to it later. I'll highlight it. I'm highlighting things that I want to come back to and maybe like dig a little bit deeper into and possibly create YouTube videos about. All right, let's see here. All right, so this one thing is modifying this program. So I'm just going to copy the CP, the ref memmalloc free thing here, vim it up, free and sborg C, and here it says modify the program to print out the current value of the program break after each execution of malloc. So let's bring up man sbreak. And then here, if we want to read it, we need to get back the void star current value of the program break after each execution of malloc. Okay. So we need to call malloc. So the only place that malloc is actually called is down here. So you can say print f of current break is equal to 0 or %x, new line, give it break or s break, s break 0, and bam, jump chapter 7, make build free and s break, and we'll do block size, number of allocs 1000, block size 10, 24, 0, step 1, min 500, max 1000. That's a lot of allocations. Maybe we do like 10 instead of that many. And then this needs to be like 5 to 10. Initial program break was at 1000, and it didn't. It grew. I think it grew. No. Oh, I need to do it like a long. Here. Long. Is that why I was complaining? Unsigned long. But the argument has type void star. Let me say, what is the correct format string for printing out a void star on AMD 64? Oh, P. Cool. I forgot about that. Boom. Make. Clear. Bam. Okay. Yeah, that didn't grow at all. So we gotta bump it up a notch. Let's go 1000. Well, let's see. Run the program specifying a small allocation block size. So maybe like 100 bytes. This will demonstrate that malloc doesn't employ sbreak to adjust the program. Wait a minute. It says modify program listing 7.1 to print out the current value of the program break after each execution of malloc, not before. What we got over up here? I'm gonna say there. Bam. Make clear. Okay. Run the program specifying a small allocation block size. That's pretty small, I guess. This will demonstrate that malloc doesn't employ sbreak to adjust the program break on each call, but instead periodically allocates larger chunks of memory from which it passes back small pieces to the caller. I want to say what's detective it's changed. Yeah, let's do that instead of printing it out all over the place. So let's grab this out and we're going to store it in new brk. This is going to be a void star, and we'll say sbreak up here. Before we do any of this stuff, we're going to assign that to the OG break, and then we're going to say, or say current break. cur break. And we say if cur break is not equal to new break, then we print it out, but only that then. And we say, hey, new break. We'll tab it in there. And we set cur break equal to new break, and then continue. Okay, and now we do this. Oh, make, sorry, clear. Oops. What's going on? Oh, this needs to be new break. Bam. Cool, cool, cool. Make, clear. Bam. So it got no new breaks. But if we go to like 100 maybe, yeah. Oh, and we want to compute the delta too. New break, and then we'll say comma delta. And here we do percent LD maybe. And it'll be new break minus cur break. Like that. Make. Clear. Bam. Hmm. 1,000? I mean, it's just kind of like, yeah, I'll make a little bit, make a little bit, make a little bit. Maybe we'll do it even tinier. 1,000 of those. It doesn't do any like exponential growth. If you do like that, yeah, these deltas are all the same, mostly all the same. Interesting. All right. All right. And if we go up here, we could also compute the I delta or J delta. We'll say J, we'll say cur J is equal to 0. And what was J defined at? Int, okay, int. And here we're going to say minus cur J, cur underscore J. We do it that way. And I need to do minus, not equals. Oops. And then here, cur J is equal to J. Bam. I'm gonna do maybe just like 1 byte, 10,000. Oh, and I need another thing here. Delta J is equal to percent D. There we go. Cool. All right, I think I'm done messing around with that. Let's go ahead and progress to chapter 8. I'll go ahead and get everything checked in here. Get status, get at all, CD back here, vim readme. Let's mark chapter 7 complete. And we'll start on chapter 8 here, which is users and groups. Get status here. There we go. Let's do a quick review of this. Just make sure nothing crazy is here. So source from the book. Okay, and that's my change there. All right. Okay. Finish chapter 7. Oops. Give me 1 second. I need to type in my credentials here. Alrighty. Get status, get OGA. Cool. Let's get push. Alright. On to chapter 8, users and groups. Okay. Every user has a unique login name and an associated numeric user identifier, UID. So the login names are just kind of like mapped onto the user IDs. The user IDs are the things that the kernel actually cares about. User ID and group ID. Users can belong to one or more groups. Each group also has a unique name and group identifier. The primary purpose of user and group IDs is to determine ownership of various system resources and to control the permissions granted to processes accessing those resources. For example, each file belongs to a particular user and group, and each process has a number of user and group IDs that determines who owns the process and what permissions it has when accessing a file. In this chapter, we look at the system files that are used to define the users and groups on the system, and then describe the library functions used to retrieve information from these files. We conclude with a discussion of the crypt function, which is used to encrypt and authenticate login passwords. Purchase like a one-way hash. Let's see here. I just want to look through the chapter. The password file, shadow password file, the group file, retrieving user and group information, bunch of source code, password encryption and user authentication, and that's it. Okay. The system. So it's basically like a super brief like overview of. Let me fix my camera here. Boom. Yeah, that's good enough. It seems like it's a brief overview of like users and groups. So yeah, nothing crazy. The system password file, etc password, contains one line for each user account on the system. Each line is composed of several fields separated by colons, as in the following example: mtkx 100 1100 Michael Karosk, home mtk bin bash. Boop. In order these fields as follows: login name. This is a unique name. So this is the MTK thing. Yeah. This is the unique name that the user must enter in order to log in. Often this is also called the username. We can also consider the login name to be the human readable symbolic identifier corresponding to the numeric user identifier described in a moment. Programs such as ls display this name rather than the numeric user ID associated with the file when asked to show the ownership of a file, as in ls-l. Encrypted password. Is his in here? No, X. This field contains a 13-character encrypted password, which we describe in more detail in section 8.5. If the password field contains any other string, in particular a string other than 13 characters, then logins to this account are disabled, since such a string can't represent a valid encrypted password. Note, however, that this field is ignored if shadow passwords have been enabled, which is typical. Yeah, that's what I normally see. In this case, the password field in Etsy password contains the letter X, and the encrypted password is instead stored in the shadow password file, section 8.2. If the password file field in Etsy password is empty, then no password is required to log into this account. This is true even if shadow passwords are enabled. Here we assume that passwords are encrypted using data encryption standard DES, the historical and widely used Unix password encryption scheme. It's possible to replace DES with other schemes such as MP5, which produces 128-bit message digest, the kind of hash of its output. This value is stored in a 34-character string in the password or shadow password file. MD5s, even when they wrote this, MD5s were like not the standard, like SHA-1 was, I think. Anyways, user ID. So numeric ID for the user. If the field has the value 0, then this account has super user privileges. There's normally one such account with a login name root, but you can have other accounts. I haven't tested this out yet, but you can rename the root user by changing the password file, I'm pretty sure. On Linux 2.2 and earlier, user IDs are maintained as 16-bit values, allowing the range of 0 through 65535. On Linux 2.4 and later, they are stored as 32 bits, allowing a much larger range. It is possible, but unusual, to have more than one record in the password file with the same user ID. Thus permitting multiple login names to the same user ID. This allows multiple users to access the same resource, e.g. files, using different passwords. The different login names can be associated with different sets of group IDs. Group ID, GID. This is a numeric ID of the first of the groups of which this user is a member. Further group membership for this user are defined in the system group file. Comment. This field holds text about the user. This text is displayed by various programs such as Finger. Home directory. This is the initial directory to which the user is placed after logging in. This field becomes the value of the home environment variable login shell. This program to which the control is transferred once the user is logged in. Usually this is one of the shells such as bash, but it can be any program. If the field is empty, then the login shell defaults to bin sh, the bourne shell. This field becomes the value of the shell environment variable. On standalone systems, all the password information resides in the file Etsy password. However, if we're using systems such as Network Information System, NIS, or Lightweight Directory Access Protocol, LDAP, to distribute passwords in a network environment, part or all this information resides on a remote system. As long as programs accessing password information employ the functions described later in this chapter, get PW name, get PWUID, and so on, the use of NIS or LDAP is transparent to application. Similarly, comments apply regarding the shadow password and group files discussed in the following section. I thought PAM is involved here as well. I wonder if they touch on PAM at all. The shadow password file, etc. shadow. Historical Unix systems maintained all user information, including the encrypted password, in etc. password. This presented a security problem since various unprivileged systems utilities need to have read access to other information in the password file. It had to be made readable to all users. This opened the door for password cracking programs try to encrypting large lists of likely passwords, e.g. standard dictionary words or people's names, to see if they match the encrypted passwords of the user. The shadow password file, etc. shadow, was devised as a method of preventing such attacks. The idea is that all of the non-sensitive user information resides in publicly readable password file, while encrypted passwords are maintained in the shadow password file, which is readable only by privileged programs. In addition to the login name, which provides the match to the corresponding record in the password file, and the encrypted password, the shadow password also contains a number of other security-related fields. Further details on these fields can be found in the shadow man page. We'll concern ourselves mainly with the encrypted password field, which we discuss in greater detail when looking at the crypt library function later in section 8.5. SUSV3 doesn't specify shadow passwords, and not all Unix implementations provide this feature. The group file. etc. group. For various administrative purposes, in particular controlling access to files and other system resources, it is useful to organize users into groups. The set of groups to which a user belongs is defined by a combination of the group ID field and the user's password entry, and the groups under which a user listed in the group file. This strange split of information across two files is historical in origin. The early Unix implementation, a user could be a member of only one group at a time. A user's initial group membership at login was determined by the group ID field of the password file and could be changed thereafter using new group 1 command, which required the user to supply the group password if the group was password protected. 4.2 BSD introduced the concept of multiple simultaneous group memberships, which was later standardized in POSIX 1 1990. Under this scheme, the group file listed the extra group memberships of each user. The groups command displays the groups of which the shell process is a member. Boop. Or if one or more usernames are supplied as command line arguments, then the group membership of those users. The group file as a group contains one line of each group in the system. Each line consists of 4 colon-separated fields, as in the following examples: users, x100, gambit, x100. So x, I imagine, is like the password thing, right? Do group passwords go in the shadow file as well? Because you need the group password to be able to get yourself added to the group. To add yourself to the group, I should say. Users x100, user x, gambit x106. So I'm guessing it's like group name, password, group ID, and then the usernames that are members of that group. Yep, group name. This is the name of the group, like the login name in the password file. We can control this to be human readable symbolic identifier corresponding to the numeric group identifier. Encrypted password, this field contains an optional password for the group. With the advent of multiple group memberships, group passwords are nowadays rarely used on Unix systems. Nevertheless, it is possible to place a password on a group. A privileged user can do this using gpassword command. If a user is not a member of the group, new group requests this password before starting a new shell whose group membership includes that group. If password shadowing is enabled, then this field is ignored. In this case, conventionally, it contains just the letter X, but any string, including the empty string, may appear, and the encrypted passwords are usually kept in the shadows group file. That's the G shadow, which can be accessed only by privileged users and programs. Group passwords are encrypted in a similar fashion to user passwords. Section 8.5. Group ID, GID. This is numeric ID for this group. There's normally one group defined within the group ID 0 named root. Like the Etsy password record with user ID 0, but unlike this user ID 0, this group has no special privileges. On Linux 2.2 and earlier, the group IDs are maintained as 64-bit values, allowing the range 0 to 65, 535. On Linux 2.4 and later, they are stored using 32 bits, so they get like 4 billion. User list. This is a comma separated list of names of users who are members of this group. This list consists of usernames rather than IDs, since as noted earlier, user IDs are not necessarily unique in password file. Okay, and you want each username to have their own password, even if they share a user ID. To record that the user AVR is a member of the group's users, staff, and teach, we would see the following record in the password file, AVR so-and-so, and the following records would appear in the group file. Yep. Wait a minute. So all users, if you don't have anything, the fourth field of the password record contains let's try asking AI on the Etsy groups file, Etsy group file, if the user list field is empty, does that mean all users or no users? Users whose primary group ID matches this GID are still members. Okay, that's how. Gotcha. So, AVR is a member of users, staff, and teach. Users has no members except for when the user says that it's a member. So basically every user is in this GID. Cool. Retrieving user and group information. In this section, we look at library functions that permit us to retrieve individual records from the password, shadow password, and group files, and to scan all the records in each of these files. Retrieving records in the password file, the get pw name and get pw info functions retrieve records in the password file. Both return a pointer on success or null on error. See the main text. Okay. Given a long and named name and get, well, let's get the signatures here. So get pw name, you give it the name, it gives you back the password struct. So maybe we look at what that struct looks like. So man get pw name password. Okay, man password, and this would be 5, it said. That's at file format. That's not what I wanted. Oops, that's definitely not what I wanted. This thing, password. So the struct. well, I'll just copy this stuff here. And then just say vim temp.c, paste it in here, bam. And we can go to definition on this now. And that will tell us username, hash passphrase, if shadow database, not used, see shadow h, user ID, group ID, real name, or comment, home directory shell program. Cool. All right. And then the get password user ID. You give the user ID, it gives it back. So yeah, you can look it up by name or user ID. That's basically what it says. Given the login name, the get password name function returns a pointer to the structure of the following type containing the corresponding information for the password record. All the stuff we just looked at. The PW, GECOS, and PW password fields of the password structure are not defined in are not defined in SUSV3, but are available in all Unix implementations. The password field contains valid information only if password shadowing is enabled programmatically. The simplest way to determine whether password shadowing is enabled is to follow a successful get PW name call with a call to get SP name. Described shortly to see if it returns a shadow password record for the same username. Some other implementations provide additional non-standard fields in the structure. The PW GECOS field derives its name from early Unix implementations where the field contained information that was used for communicating with a machine running the General Electric Comprehensive Operating System. Although this usage has long since become obsolete, the field name has survived, and the field is used for recording information about the user. The get PW UID function returns exactly the same information as get PW name, but does a lookup using the numeric user ID supplied in the argument UID. Both get PW name and get PW UID return a pointer to a statically allocated structure. This structure is overwritten on each call to either of these functions or to the get PWENT function described below. Boop. Okay. I don't really feel like reading all this right now. Alright, I'm going to take a little bit of a break here. Let's see how long I've been streaming for. Let's see. 2 hours. Okay. I think I got a lot done. 2 hours. Finished the chapter on memory and read half of the chapter here on the users and groups. But this stuff is boring me and I need to get some food in me, so I'm going to take a little bit of a break. But I will be back here probably in about 45 minutes to finish reading some of this stuff this evening. All right, I'll be back.